Space has a bottom, a point where the rulers run out, where measuring anything smaller destroys the measurement. That point is called the Planck length. It is 100 trillion times smaller than an inch. At that scale, quantum physics and Einstein's gravity crash into each other, and both collapse. We will visit the foam boiling at the edge of space, the black holes that erase their own evidence, and the question that may never have an answer: is reality made of smooth fabric or tiny unbreakable pixels? If you enjoy the journey, subscribe and hit like. Let's begin. There is a number so small that the universe itself refuses to let you go smaller. You cannot see it, you cannot touch it, no microscope, no telescope, no machine ever built by human hands can reach it. And yet physicists are almost certain it exists. They call it the Planck length. And once you understand what it is, you will never think about space, distance, or reality the same way again. Here is the strange part. The Planck length did not come from an experiment. No scientist measured it in a lab. It came from a desk, from a man staring at equations and noticing something odd hiding inside the math. The number itself looks absurd. Written out, it is roughly 1.6 times 10 to the negative 35th meters. That means nothing by itself. So let's make it real. Take an inch, divide it by 100 trillion, now divide that by 100 trillion again, then divide it one more time by 10 billion. You are getting close. The Planck length is that inconceivably small, compared to a proton, which is already one of the smallest things humans have ever directly measured. The Planck length is 100 billion trillion times smaller. To put that another way, if you took a single proton and blew it up until it was as wide as the entire observable universe, 93 billion light-years across, then the Planck length, scaled up by the same amount, would still only be the size of a proton. That comparison is confirmed by physics. That is the actual ratio. So why does this number matter? Why do physicists treat it like a wall at the bottom of reality? Because of what happens when you try to go smaller. Every measurement in science works by throwing something at something else and seeing what bounces back. You probe a virus with light, you probe an atom with electrons, you probe a proton with other protons smashed together at nearly the speed of light. The smaller the thing you want to see, the more energy you need in your probe. That is a confirmed rule of physics. It has never been broken. Follow that rule all the way down to the Planck length, and something terrifying happens. The energy required to probe that distance becomes so enormous that the probe itself collapses into a black hole. The act of measuring creates a black hole exactly as wide as the distance you are trying to measure. The universe swallows the answer. That is not a limitation of our technology. It is not something a better microscope would fix. It follows directly from combining two of the most tested, most trusted theories in all of science. The energy required to probe Planck distances from quantum mechanics, the black hole that forms when that energy is concentrated, from general relativity. Both laws together make measurement at this scale physically impossible. Some physicists say this means the Planck length is a true minimum, a hard edge, the smallest distance that can meaningfully exist. Others say it is only a measurement limit and that something might exist below it, permanently hidden from us forever. Both possibilities are terrifying in their own way. And the story of how one quiet German physicist stumbled onto this wall more than a century ago without even trying to find it is even stranger than the wall itself. The year was 1899. A German physicist named Max Planck was not trying to find the edge of reality. He was doing something far more ordinary. He was trying to clean up a mess in the math. At the time, physicists were studying how objects glow when heated. Everyone knew the observations: a piece of metal heats up, turns red, then orange, then white. But the equations of the day produced a disaster when applied to this problem. At short wavelengths, the math predicted that a glowing object should release infinite energy. Infinite. Every hot object in the universe should be pumping out endless amounts of radiation. That obviously did not happen. The equations were wrong, and everyone knew it. Planck fixed the problem by introducing a correction. He proposed that energy does not flow in smooth, continuous streams. It comes in tiny packets, chunks, minimum units he called quanta. It was a radical idea, and Planck himself was uncomfortable with it. He thought it was a temporary mathematical trick, not a description of physical reality. But tucked inside that same paper, almost as a side note, Planck did something else. He noticed that three constants of nature, numbers that appear in the fundamental laws of physics, could be combined in a specific way to produce a unit of length. The gravitational constant, which describes the strength of gravity, the speed of light, which governs all motion and energy, and his own new constant, which governs the scale of quantum behavior. Combine those three, take their square root in a particular arrangement. Out comes a length, one specific, unavoidable length. Planck called it a natural unit because it was not based on any human convention, no arbitrary choice of what to call a meter or a foot. Any civilization anywhere in the universe, using those same three constants, would calculate the exact same number. He presented it to the Prussian Academy of Sciences in May of 1899. He described it as a unit meaningful to any intelligent beings, even extraterrestrial ones. Then he moved on. For decades, almost nobody cared. The Planck length sat in the math like a quiet footnote, too small to measure, too abstract to explain. Physicists had bigger problems to solve. Quantum mechanics was built into a full theory. Einstein published general relativity. And slowly, painfully, physicists began to realize that those two great theories could not coexist at small scales. The smaller the scale, the more violently they disagreed. And at the exact scale Planck had calculated from pure math in 1899, both theories broke down completely. He had found the wall without knowing there was a wall. That is the part that should unsettle you. Planck was not hunting for a fundamental limit. He was patching an equation about glowing metal. And the number he wrote in the margin of that calculation turned out to mark the boundary where all of modern physics stops working. Scientists today describe Planck's natural units as universal, confirmed. Built into the structure of nature itself, the length was always there. He just noticed it first. And what sits at that length is far stranger than a simple boundary. Because when two of the most powerful theories in history meet at this scale, the collision is spectacular. Before you can understand why the Planck length breaks physics, you need to feel how small it actually is. Scale is the hardest thing for the human brain to handle. We evolved to think in feet and miles. Our gut-level sense of size works well for things between the size of a grain of sand and the size of a city. Outside that range, numbers stop feeling real. So let's walk down together, one step at a time. Start where you are. You are roughly 6 feet tall. A grain of sand is about 1/10,000th of a foot wide. That feels small. A human hair is about the width of 10 grains of sand laid side by side. Still manageable. Now go smaller. A red blood cell is about 1,000 times thinner than a human hair. You cannot see it with the naked eye, but a decent microscope handles it easily. Go 10 times smaller than that, and you reach a bacterium. Still technically visible under a microscope. Keep going. A virus is roughly 100 times smaller than a bacterium. An atom is about 10 times smaller than a virus. We are now at scales no optical microscope can see. To probe an atom, you need an electron microscope, or you need to fire particles at it and measure how they bounce. Go deeper. Inside the atom sits the nucleus. The nucleus is 100,000 times smaller than the atom itself. If an atom were the size of a football stadium, the nucleus would be a grain of sand in the center. Inside the nucleus sit protons. A proton is about 1/10,000th the width of the nucleus. At this point, we have reached the edge of what humans have directly measured. Protons are about 1/4,000,000th of a meter wide. That is already so small it feels fictional. The Planck length is 100 billion trillion times smaller than a proton. Read that again. A proton is already almost impossibly small. The Planck length is 100 billion trillion times smaller than that. Here is the comparison that physicists actually use to make this real. If a proton were the size of the observable universe, 93 billion light-years from edge to edge, the Planck length scaled up by the same amount would still only be the size of a proton. The Planck length is to a proton what a proton is to the entire visible cosmos. That ratio is confirmed. That is the actual math. Now here is where it gets strange. The most powerful particle accelerator ever built, the Large Hadron Collider near Geneva, Switzerland, smashes protons together at nearly the speed of light. Its highest collision energies probe distances about 1,000 times smaller than a proton. That sounds impressive, and it is. But the Planck length sits 100 trillion times smaller than even that. The collider that would need to exist to probe the Planck scale directly would require energies so extreme that the machine would need to be larger than the observable universe itself. That is confirmed by the physics. The numbers are not even close. We have never directly observed anything at the Planck scale. We likely never will. And yet, physics tells us something extraordinary is happening there. Something that involves the deepest rules of reality. To understand why, you need to understand what 3 specific numbers have to do with the end of all measurement. Some numbers in physics are chosen by humans: a meter, a pound, a second. We invented those for convenience, and on another planet, another civilization would have picked different ones. But some numbers in physics are not chosen. They are found. They show up in the equations whether you want them or not. You cannot change them. You cannot argue with them. They are baked into the structure of the universe, and every civilization anywhere in existence would calculate the exact same values. 3 of those constants, when you combine them in a specific way, produce the Planck length. Understanding what each one describes is the key to understanding why the Planck length is so fundamental. The first is the gravitational constant. Call it G. It governs how strongly mass pulls on other mass. It shows up in every calculation involving gravity, from the orbit of the moon to the collapse of a star into a black hole. It is confirmed by centuries of measurement. The second is the speed of light. Every particle of light, every photon, crosses about 186,000 miles every second in empty space. That number does not change, ever, for anything. It is confirmed in experiment after experiment and sits at the heart of Einstein's entire theory of relativity. The third is the Planck constant, the number that governs quantum behavior. It sets the scale at which quantum effects become important. Below a certain size, particles stop behaving like tiny billiard balls and start behaving like waves, existing in multiple places at once, tunneling through walls, refusing to have a definite position. The Planck constant tells you where that weirdness kicks in. Now here is the remarkable thing. These 3 constants describe completely different aspects of reality. Gravity is a large-scale cosmic force. The speed of light is a universal speed limit. Quantum behavior happens at atomic and subatomic scales. They seem unrelated. But when you combine them mathematically, something unexpected happens. Take the Planck constant, multiply it by the gravitational constant, divide by the cube of the speed of light. Take the square root, out comes a length. One precise, specific, unavoidable length. The Planck length. That formula is confirmed physics. It is not theoretical guesswork. And here is why that matters so much. The Planck length is not defined by any one of these forces. It emerges from all 3 simultaneously. It is the scale where gravity, quantum behavior, and the speed of light all become equally important at the same time. Below that length, you cannot ignore any of them. You cannot use quantum mechanics without gravity destroying the calculation. You cannot use gravity without quantum effects collapsing the math. All 3 constants demand attention at once, and no current theory can handle all 3 together. That is the collision. Max Planck saw the length in the math. He did not know what it meant. The physicists who came after him eventually understood. The Planck length is the point where the two greatest theories in the history of science, theories that each work with stunning precision in their own territory, arrive at the same address and tear each other apart. That collision is the next thing you need to see, and it is not a gentle disagreement. Two theories run the universe. They are the most tested, most precise, most spectacularly successful ideas in the history of science. Both have survived every experiment thrown at them for over a century. Both make predictions so accurate they would be like predicting the distance from New York to Los Angeles, correct to within the width of a human hair. And they cannot coexist. The first is quantum mechanics. It governs everything at the scale of atoms and below. At that scale, particles do not have fixed positions. They exist in clouds of probability. A single electron is not sitting in one place. It is smeared across a range of possible locations, and the moment you measure it, the cloud collapses to a specific point. The universe at small scales is fuzzy, uncertain, and probabilistic by nature. That is not a flaw in our measurements. It is how reality works down there, confirmed by thousands of experiments. The second is general relativity. It governs everything at the scale of large masses and high speeds. Gravity, in this picture, is not a force. It is a bend in the fabric of space and time. A massive object like the sun curves the space-time around it, and the Earth follows that curve the way a marble rolls around the edge of a funnel. Space-time in this theory is smooth, continuous, and perfectly well defined at every point, also confirmed by thousands of experiments, including the detection of gravitational waves. In most situations, you pick one theory or the other and use it. Quantum mechanics for atoms, general relativity for black holes, and galaxies. They live in different size ranges, and you almost never need both at once. Almost never. At the Planck length, you need both. You cannot avoid either one. And when you apply them together, the math explodes. Here is the core of the problem. General relativity describes space-time as a smooth surface, smooth all the way down to any scale you choose. Quantum mechanics says that smooth surfaces at small scales are impossible. At tiny scales, quantum uncertainty causes violent fluctuations in energy. Apply that to space-time itself, and space-time stops being smooth. It becomes wildly turbulent, bubbling, tearing, undefined. But general relativity requires space-time to be smooth in order to work at all. If space-time is turbulent, Einstein's equations produce nonsense. Division by zero, infinite curvature. The math breaks. Flip the direction, and the same disaster happens. Quantum mechanics has its own mathematical engine, a technique for calculating physical predictions by adding up series of corrections. At normal scales, those corrections get smaller and smaller, and the series adds up cleanly. At the Planck scale, the corrections blow up. They become larger than the main answer. The series stops adding up. The engine stalls. Both frameworks collapse at the same scale, independently, for separate reasons. Physicists have been trying to reconcile this for over 50 years. Every attempt runs into the same wall, and the wall has a very specific address, the Planck length. The next clue to why comes from a rule of physics so strange, so counterintuitive, that even the people who discovered it found it hard to accept. In 1927, a young German physicist named Werner Heisenberg proved something that still bothers people a century later. You cannot know exactly where something is and exactly how fast it is moving at the same time. Try to pin down the position more precisely, and the momentum becomes more uncertain. Try to pin down the momentum, and the position blurs. The more precisely you nail one, the more the other escapes. This is the Heisenberg uncertainty principle, and it is confirmed. Tested, built into the foundation of quantum mechanics. This is not about bad equipment. Heisenberg was not saying our rulers are too clumsy or our cameras too slow. He was saying that the universe itself does not allow both pieces of information to exist at once, at full precision, for any particle. Now here is where it connects to the Planck length. Every measurement in physics works by probing something with something else. To see a proton, you fire a particle at it with enough energy to reach proton-sized scales. The energy of the probe determines the smallest distance you can examine. Higher energy means shorter wavelength means smaller scale visible. That is confirmed quantum mechanics. Now apply this logic all the way down. You want to probe a distance smaller and smaller, approaching the Planck length. You need a probe particle with a shorter and shorter wavelength. Shorter wavelength means higher energy. That is not a technical problem. That is a law of nature. So you pack more and more energy into your probe. The energy climbs. The probe gets more precise. You approach the Planck scale. Here is the trap. Heisenberg's principle says that confining a particle to a very small region means its momentum must be very uncertain. Uncertain momentum means uncertain energy. At the Planck scale, the uncertainty in the probe's energy becomes so enormous that the probe carries energy comparable to an entire star compressed into a space 100 billion trillion times smaller than a proton. And general relativity, perfectly reliable as always, tells you exactly what happens when you compress that much energy into that smaller space. A black hole forms. The probe particle collapses into a microscopic black hole. The black hole immediately swallows the information you were trying to gather. The measurement destroys itself. This is the Heisenberg trap at Planck scales. The harder you push to measure, the more the universe pushes back. At every larger scale, better tools give better results. At the Planck scale, better tools create bigger black holes and less information. Some physicists describe this as the universe enforcing its own privacy. The Planck length is where nature draws a curtain. But here is what nobody agrees on. Is that curtain a wall, or is it a door? Does something exist beyond it? Something real, something physical, permanently hidden from observation? Or does the concept of distance simply stop meaning anything below this scale? The way the question, what is north of the North Pole, stops meaning anything. Two very different answers to that question lead to two very different pictures of what reality is made of. But both pictures must first pass through the same terrifying bottleneck, the moment when any attempt to probe the Planck length creates the smallest black holes in the universe. Imagine trying to take a photograph so precise that the camera destroys itself the moment you press the shutter. That is the situation at the Planck length. The logic is clean, painful, but clean. To observe something at the Planck scale, you need a probe with a wavelength at that scale. Wavelength and energy are locked together in quantum mechanics. Shorter wavelength, higher energy. At the Planck scale, the required energy corresponds to what physicists call the Planck mass, roughly 22 micrograms. 22 micrograms sounds almost nothing. It is roughly the mass of a single grain of fine sand. But you are not spreading that mass across a grain of sand. You are compressing it into a volume 100 billion trillion times smaller than a proton. General relativity has a precise formula for what happens in that situation. A region of space with that much energy compressed into that smaller volume collapses under its own gravity. Instantly, the probe becomes a black hole. The black hole that forms has a radius equal to the Planck length, the exact distance you were trying to measure. The probe becomes the wall. The measurement creates the thing that makes measurement impossible. This has a specific name in physics. Some researchers call it the ultraviolet self-completeness of gravity. The idea is that nature censors itself. Any attempt to probe scales below the Planck length generates a gravitational collapse that hides the result. The signal never reaches the outside world. The universe writes the answer and immediately seals the envelope. This is confirmed in the sense that it follows directly from combining quantum mechanics and general relativity, both of which are confirmed theories. No experiment has probed the Planck scale, so no experiment has directly verified this prediction. But the logic is solid enough that nearly all physicists accept it. Now consider what this means for the nature of space. If no signal can ever arrive from below the Planck scale, then the concept of subplanckian distances may be physically empty, physically meaningless, like asking what temperature is colder than absolute zero. The question is grammatically valid, but the universe does not contain an answer. Physicists have tried to work around this in creative ways. What if you used gravity waves instead of particles as your probe? Still runs into the same energy limit. What if you used pairs of entangled particles? Same problem from a different angle. What if you used the geometry of space itself as your measurement tool? At this scale, the geometry is what breaks down. Every door leads to the same room. The black hole factory is not a design flaw. It looks like a feature, a hard stop built into the structure of nature at one specific scale. And that scale has a corresponding moment in time. If distance has a flaw, time has one too. A smallest possible tick, a unit so short that nothing can happen inside it, because inside it may not exist, and understanding it takes the strangeness somewhere even harder to imagine. Distance and time are not separate things. Einstein proved that more than a century ago. Space and time are woven together into a single fabric. Stretch space and you stretch time. Compress space and time changes too. They move together. They break together. So if the Planck length is the smallest meaningful distance, then time has its own version, the smallest meaningful tick. It is called Planck time, and it is the time it takes light traveling at 186,000 miles per second to cross one Planck length. Since the Planck length is so inconceivably small, the time it takes light to cross it is correspondingly inconceivable. Planck time is approximately 5 times 10 to the negative 44th seconds, spelled out 0.000, followed by 43 more zeros, then a 5. The human blink of an eye takes about 300 milliseconds. 1 millisecond is already a thousandth of a second. 1 millionth of a millisecond gets you to the scale of some chemical reactions. Keep dividing by 1,000. Again and again. More than 10 times over, and you still have not reached the Planck time. The best atomic clocks humans have ever built are accurate to about 1/10,000,000th of a trillionth of a second. Those are the most precise timekeepers in history. The Planck time is still 25 orders of magnitude shorter than that. The gap between the finest clock ever made and the fundamental tick of the universe is larger than the gap between 1 second and the entire age of the universe. So what happens inside a Planck time tick? Physics says the honest answer is, we do not know. At the Planck time, the same collision between quantum mechanics and general relativity that destroys distance also destroys time. The concept of a moment requires a geometry of space-time to sit inside. Below the Planck time, that geometry stops being defined. Some physicists argue that time is discrete, that events do not flow in a smooth, continuous stream the way a river flows. Instead, reality ticks forward in Planck time steps, like frames in a film. Between frames, nothing is happening. There is no between. The movie only exists frame by frame. Others argue that time remains continuous, but simply becomes unmeasurable below the Planck time. The river still flows, but below a certain depth, no instrument can touch it. Both views are theoretical. Neither is confirmed by experiment. The Planck time is so far below the reach of current technology that direct testing may never be possible. But the Planck time carries a consequence that reaches all the way back to the first moment of the universe, because the Big Bang itself hit this limit. And what lies on the other side of that limit is the deepest mystery in all of cosmology. If you run the universe backward, everything gets smaller and hotter. Galaxies pull together, stars compress. Matter collapses inward. The further back you go, the denser and more energetic everything becomes. Cosmologists can trace this backward with stunning precision, confirmed by observations of the cosmic microwave background, the ancient light filling the entire sky, and by the measured abundances of hydrogen and helium forged in the first minutes. The equations work beautifully, right up until a wall. The wall arrives at the Planck time after the Big Bang, roughly 5 times 10 to the negative 44th seconds after the moment of beginning. Before that tick, the universe was so hot, so dense, and so compressed that the energy concentrated in every cubic Planck length of space exceeded the Planck energy. Quantum gravity effects became dominant. General relativity and quantum mechanics both stopped producing coherent predictions at that point. Physics goes silent. Cosmologists call this the Planck epoch, the first Planck time tick of existence. Everything before it is a wall of mathematical noise. Standard cosmology cannot describe it. No current theory can describe it. This means that when someone asks what happened before the Big Bang, the answer is not nothing. The answer is, the question cannot be answered with any tool we currently have. Time itself, as we define it, may not extend backward through the Planck epoch. The concept of before may stop working the way north stops working when you reach the North Pole. Some approaches in quantum cosmology try to get around this. Loop quantum cosmology, a theoretical framework, proposes that the universe did not begin from a true singularity. Instead of a point of infinite density, the universe reached a maximum compression and then bounced. In this picture, the Planck epoch is not the beginning of time. It is the moment of maximum squeeze in an ongoing process. Time extends backward through it into a previous contracting universe. That is a theory, unconfirmed, contested. Other physicists take inflation, the idea that the universe expanded at incredible speed in its first fractions of a second, and push it as close to the Planck epoch as the math allows. Inflation explains why the universe looks the same in all directions, why the cosmic microwave background is so smooth, and why large-scale structures like galaxy clusters formed. The equations of inflation work, but they must stop just before the Planck epoch. And here is the detail that should disturb you. The quantum fluctuations that inflation stretched into the seeds of every galaxy, every star, every planet including Earth, may have originated at scales smaller than the Planck length. If so, the large-scale structure of the entire universe carries an imprint of physics that happened below the Planck scale. Every galaxy is a stretched-out signature of an event we cannot directly describe. That is the Transplanckian problem. Unresolved. Open. A reminder that the observable universe may be a projection of something that happened where our theories break down. And down at that scale below the Planck length, space itself may be doing something nobody expected. Something that looks nothing like the smooth, quiet emptiness we imagine. In 1955, a physicist named John Wheeler sat down and asked a question nobody had thought to take seriously before. What does space actually look like at the Planck scale? Not what equations say about it from a distance. What does it look like if you zoom all the way in? Wheeler approached it with an analogy. Picture the ocean from an airplane at 30,000 feet. From up there, it looks flat, smooth, almost like a mirror. Drop closer, and waves appear. Swells, troughs, motion. Climb down into a life raft on the surface, and the picture changes entirely. The ocean is churning foam, bubbles forming and breaking. The surface is never still. It is constantly creating and destroying tiny structures faster than you can count them. Wheeler argued that space-time is exactly like that ocean. From our scale, the universe looks smooth. Space-time appears perfectly flat, calm, and well-behaved. Zoom down to atomic scales, and you see small ripples, the quantum fluctuations of matter and energy. But zoom all the way down to the Planck scale, and space-time itself becomes foam. He called it space-time foam. The idea works like this. Quantum mechanics applies the Heisenberg uncertainty principle not just to particles but to the very fabric of space. At the Planck scale, the uncertainty in the geometry of space becomes enormous. Space-time does not hold a fixed shape. It fluctuates wildly. The curvature of space, which in general relativity is determined by energy, becomes violently uncertain. Space cannot maintain a stable structure at this scale. Wheeler proposed that at the Planck scale, tiny wormholes, tunnels connecting distant regions of space, might blink in and out of existence in less than a Planck time. The topology of space, its fundamental shape and connectivity, might change from one tick to the next. Regions might disconnect and reconnect. Space-time might fold, bubble, and split in ways that have no equivalent at any larger scale, and then smooth out again. From a distance, all of that violence averages away. Space looks calm, flat, continuous. That is the theory. It is compelling, mathematically motivated, and has been taken seriously by physicists for decades. But it has a problem. Nobody has ever seen it. At first, that seems unsurprising. The Planck scale is unreachable. Of course, nobody has seen it directly. But space-time foam makes a prediction that should be testable indirectly. If space is churning at the Planck scale, then light traveling through it should be affected. Photons should pick up tiny random delays. Different wavelengths of light should arrive from distant sources at slightly different times, scrambled by the foam they passed through. Astronomers have looked for exactly that signal in light from distant quasars and gamma-ray bursts. Billions of light-years of travel time, giving the effect billions of years to accumulate. And the results were surprising in a very specific way. Stay with the foam for a moment longer, because Wheeler's idea, once it took root, grew into something even stranger than the original proposal. If space-time is churning at the Planck scale, the foam is not just rough and turbulent. The turbulence involves the topology of space itself. Topology is the mathematical study of how things are connected. A sphere and a cube have the same topology because you can reshape one into the other without cutting. A donut and a sphere have different topologies because the hole in the donut cannot be smoothed away. At ordinary scales, the topology of space is fixed. You cannot create a hole in the fabric of the universe by staring at it hard enough. Space is simply connected. One region, no tunnels, no shortcuts. Wheeler proposed that at the Planck scale that stability disappears. Quantum uncertainty in the geometry of space becomes large enough to change the topology from moment to moment. A tunnel might appear between two distant regions of space, a tiny wormhole, exist for less than one Planck time, and then vanish as if it never happened. One Planck time, remember, is 25 orders of magnitude shorter than the best atomic clock can measure. These wormholes do not last long enough to be detected by any instrument, carried through by any signal, or used as shortcuts by anything. They flicker in and out of the geometry of space too fast for the concept of lasting to apply. At scales larger than the Planck length, all of this averages out. The trillions upon trillions of these micro-events per Planck cancel each other out, and space-time looks smooth, like the flat ocean seen from 30,000 feet. This is a theory, compelling but unconfirmed, and here is where the physics gets genuinely uncomfortable. If space-time foam is real, it should leave marks. Light traveling across billions of light-years passes through an ocean of this foam. Photons of different energies would interact with the foam slightly differently. Short wavelength, high-energy photons might accumulate tiny delays differently than long-wavelength, low-energy photons. Over billions of light-years, those tiny differences might stack up enough to be measured. Astronomers aimed the best telescopes on Earth and in orbit at some of the most distant, most energetic sources in the sky, gamma-ray bursts, and quasars billions of light-years away. The goal was to find arrival time differences between photons of different energies that could only be explained by space-time foam. They found no such difference. Zero. Space looked perfectly smooth, down to scales far smaller than most simple foam models predicted. Some foam models survived those null results. the simpler versions did not. Space-time foam, if it exists, is either far subtler than Wheeler's original picture, or the fluctuations do not produce the kind of signal those observations could detect. The search continues, and the absence of a signal is not proof of absence. The most precise telescopes ever built are still laughably coarse compared to the Planck scale. But the hunt left scientists with a new question. If foam exists and leaves no detectable trace, how would we ever know? And that question led to one of the most creative experiments in the history of physics. Scientists decided to use the universe itself as the measurement instrument. The idea was elegant. You cannot probe the Planck scale directly with any machine built on Earth, but light from a quasar 12 billion light-years away has been traveling for 12 billion years. If space-time is foamy at the Planck scale, that foam is everywhere, and the light has been swimming through it the entire time. Tiny effects given enough distance can accumulate. A delay so small it is invisible, over 1 mile, becomes measurable over 12 billion light-years. That is the principle behind these observations. The specific prediction from space-time foam models goes like this. High-energy photons, the ones with short wavelengths and high energies, should interact with space-time foam differently than low-energy photons. If foam fluctuations smear or delay photons at the Planck scale, then a burst of gamma rays arriving from a distant quasar, or gamma-ray burst, should show its high-energy photons arriving at slightly different times than its low-energy photons. The spread in arrival times would be the signature. NASA's Fermi Gamma Ray Space Telescope was perfectly suited for this test. Fermi detects gamma-ray bursts from across the observable universe and measures the arrival times of individual photons with great precision. Scientists use data from hundreds of gamma-ray bursts and distant blazars, the energetic jets from supermassive black holes. The result? No detectable difference. High-energy and low-energy photons arrive together within the measurement precision of the telescope. This ruled out the simplest class of space-time foam models, the models that predicted the largest effects, the ones called random walk foam models, were effectively eliminated. Space, as seen through these photons, behaved as if it was smoothed down to scales far below a proton. A similar search used the Chandra X-ray Observatory. Astronomers examined the apparent sizes of distant quasars in X-ray wavelengths. If space-time foam blurs light as it travels, distant point sources should appear slightly smeared. Chandra found no smearing. Quasars billions of light-years away appeared as sharp as their physics permitted. These are confirmed observational results. They do not prove space-time foam is wrong. They prove that if foam exists, its effects are smaller or different in character than the leading models predicted. Some refined foam models survive. They predict effects that those telescopes could not have detected with their specific methods. The question remains open, but the null results carry their own kind of power. They push the boundaries, they narrow the possibilities, and they remind you that the universe, when asked a question by a well-aimed telescope, sometimes answers with silence, and silence is data too. There is a deeper question hiding behind the foam debate. The foam question asks whether space is turbulent at the Planck scale. A more fundamental question asks whether space has a Planck scale at all in the way physicists assume, whether it is made of indivisible chunks, whether reality is continuous or pixelated. Everything you can see right now is made of chunks. Your screen appears smooth, but zoom in and it is pixels. Your desk appears solid, but zoom in and it is atoms, then smaller particles, then mostly empty space. The world keeps revealing structure at smaller and smaller scales, chunks all the way down. The question is whether that pattern has a stopping point. A continuous universe would mean space and time are infinitely divisible. Between any 2 points, no matter how close, there is always another point, always a shorter distance possible. This is how general relativity treats space-time. Smooth, continuous, infinitely refined. A discrete universe would mean there is a smallest chunk, a minimum distance, a minimum time, a pixel size for reality itself. Below that pixel, nothing exists. Distance stops being meaningful. The Planck length is the natural candidate for that pixel size. If space is discrete at the Planck scale, the consequences are profound. Motion itself would change character. An object moving from one point to another would not pass through infinitely many intermediate positions. It would jump from one Planck scale pixel to the next, with no physical state in between. The universe would process reality the way a computer processes information, one tick at a time, one minimum step at a time. This picture would resolve something that has troubled mathematicians since ancient Greece. Zeno of Elea, a philosopher who lived about 2,500 years ago, posed a paradox that became famous. To walk across a room, you first cover half the distance, then half of what remains, then half of that. You always have half the remaining distance still to go. The series of halvings never ends, so how does anyone ever arrive anywhere? Mathematicians resolved Zeno's paradox using the concept of convergent series. Infinite steps, but a finite sum. The math works out. You do arrive. But if space is discrete at the Planck scale, the paradox dissolves in a different way. The halvings do not continue forever. At some point you reach one Planck length remaining. You cannot halve it. The next step carries you across it entirely. The infinite regress hits a floor and stops. Whether this is what actually happens is unknown. Physics has not confirmed that space is discrete. General relativity assumes it is continuous, and experiments have not yet probed small enough scales to detect granularity. The Planck scale remains far beyond current experimental reach. But one theory of physics makes a specific detailed prediction that space is discrete at exactly this scale, and it describes what those discrete chunks look like with surprising precision. The theory is called loop quantum gravity, and the picture it paints of reality's deepest structure is unlike anything in ordinary experience. What if space is not a background? What if space is made of something? In general relativity, space is the stage. Matter and energy move around on it. But the stage itself is just there, smooth, passive, always present. Loop quantum gravity flips this completely. In this theory, space is made of actual physical structures, quantized loops of geometry woven together into a network. The background is the thing, and like all quantum things, it comes in minimum units that cannot be divided further. The picture that emerges is called a spin network. Imagine a chain-link fence. The fence has nodes where wires cross, and links connecting them. Now make the fence three-dimensional. Now make it the entire universe. Each node in the spin network represents a minimum volume of space, roughly 1 Planck volume, a cube with sides 1 Planck length long. Each link between nodes represents a minimum area of space, roughly 1 Planck area, the square of the Planck length. Space, in this framework, is this network. The nodes are the atoms of space. The links are the atoms of surface. Between nodes, there is no space. There is no between. The network is space, and space is the network. It is a well-developed one, with equations and predictions developed over decades by a large community of physicists, but it has not been confirmed by experiment. The predictions it makes are extraordinary. Volumes are quantized. Areas are quantized. No volume in the universe can be smaller than 1 Planck volume. No area can be smaller than 1 Planck area. These are hard limits, built into the fabric of space itself, the way the charge of an electron is a hard limit on electric charge. Time in loop quantum gravity works the same way. The universe does not evolve continuously, it ticks forward in Planck time steps. Each tick, the spin network updates. New links form, old ones dissolve, nodes merge and split. Every physical event is a rearrangement of this network, and the minimum interval between events is 1 Planck time. The deepest implication is this: if loop quantum gravity is correct, then the smooth space-time of general relativity is an illusion that appears at large scales the way a smooth foam mattress appears solid from across the room. Zoom in far enough and you find the springs. At the Planck scale, you find the spin network. And here is the connection that should make this click. Every particle of matter you have ever encountered, every photon of light, every force carrier, every quantum field, exists on top of this network. Reality is not matter sitting in space. Reality is matter and space together, built from the same Planck scale fabric. If this picture is right, then Zeno's ancient paradox was not just a mathematical puzzle. It was pointing at a physical truth about the structure of space. And that truth comes with something ancient Greece never imagined. Zeno was not trying to prove that motion is impossible. He was trying to force people to confront something uncomfortable about the nature of infinity. His most famous paradox goes like this. You want to walk from where you are to a wall 10 feet away. Before you reach the wall, you must reach the halfway point, 5 feet. Before you reach that, you must reach the halfway point of 5 feet, 2.5 feet, and so on. Always a halfway point before the next halfway point. An infinite series of steps before you arrive anywhere. And yet, you arrive. You walk to walls all the time. So, what is going on? Mathematics solved this for practical purposes about 2,000 years later. An infinite series of numbers can add up to a finite total if the numbers shrink fast enough. 1/2 plus 1/4 plus 1/8, continuing forever, adds up to exactly 1. The math works. Zeno's steps sum to a finite distance. You arrive. But mathematics, solving the arithmetic, does not tell you whether the physical steps themselves are real. Does space actually have infinitely many halfway points between two locations? Or does it have a finite number of discrete positions? If loop quantum gravity is correct, the answer is finite. The halfway points do not go on forever. They stop at the Planck length. Below that scale, there is no halfway. The concept of distance stops applying. The network has no smaller node. This means motion at the deepest level looks like jumping between adjacent nodes on the spin network. An electron moving across a room is not tracing a smooth continuous path through infinite intermediate positions. It is hopping from node to node, Planck length by Planck length, in discrete quantum steps. This is a theory, unconfirmed, but it raises a question worth sitting with. If the universe is discrete at the Planck scale, is it also, in some sense, computable? Does the universe run like a computation, updating state by state, tick by tick, with a specific resolution? Some physicists take this possibility seriously. The universe would then have a maximum information density, 1 bit per Planck volume. Every region of space would have a finite number of possible states, determined by how many Planck volumes it contains. Reality would be digital at its foundation. Others push back hard on this. General relativity, tested to extraordinary precision, assumes space is smooth and continuous. No experiment has ever detected any sign of discreteness. Zeno's paradox, they argue, was solved cleanly by mathematics and requires no appeal to Planck scale physics. The debate is real, active, unresolved. What is clear is this. Both sides agree that the Planck length is where the question lives. If space is discrete, the pixel is Planck-sized. If space is continuous, the limit of that continuity is still the Planck length, where measurement becomes impossible. And an entirely different theory of physics, one that has dominated theoretical physics for 4 decades, has its own answer to where space's structure bottoms out. An answer that does not quantize space at all. An answer that says the pixels are wrong. What you need instead are strings. Everything in the universe, every electron, every quark, every photon, every force, is a point. That is the assumption baked into the standard model of particle physics, the most successful theory of matter ever built. Particles are infinitely small, zero size, perfect mathematical points. And that assumption quietly causes a catastrophe. When you calculate the energy of a point particle by adding up quantum corrections, the corrections blow up. Infinite energy, infinite mass, infinities everywhere. Physicists developed a technique called renormalization to manage this. You absorb the infinities into the measured values of things like mass and charge, and the predictions come out finite and correct. It works, but it feels like a patch over a leak. String theory tears out the patch and fixes the leak. It says particles are not points. They are tiny one-dimensional loops of vibrating energy. Strings. Each string vibrates at a specific frequency, and the frequency determines what kind of particle it is. An electron is a string vibrating one way. A photon is a string vibrating another way. The graviton, the particle that carries gravity, is a string vibrating a third way. And this is where the Planck length comes back in. The size of these strings is expected to be close to the Planck length. One Planck length long, give or take a factor of a few. When two strings interact, their minimum spatial resolution is set by their own size. You cannot probe a distance smaller than the string by using the string as your probe. The string cannot fold back on itself beyond a certain scale. So string theory introduces its own minimum length, comparable to the Planck length, through the physical size of the strings rather than through quantizing space itself. This distinction matters. In loop quantum gravity, space itself is granular. It comes in Planck-sized chunks. The network of space has a smallest node. In string theory, space remains continuous, but the objects moving through it have a minimum size. You cannot resolve anything below that size using any string-based interaction. The granularity is in the matter, not the space. Both arrive at the same practical flaw, the Planck length. But they disagree deeply about what is granular. String theory also has a remarkable mathematical property called T-duality. If you compactify one of the extra dimensions that string theory requires, a dimension curled into a tiny circle, then physics, at a radius smaller than the string length, turns out to be mathematically identical to physics at a radius larger than the string length. Small and large swap roles. A universe compactified to below the string length is physically equivalent to one compactified to above it. The concept of smaller than the string length does not point to a new physical regime. It maps back to something already described. The question of what happens below the Planck scale in string theory might dissolve rather than get answered. But even string theory faces a wall so large it defines the entire field. To test it directly, to actually observe a string, you would need to probe the Planck scale, and the scale of energy required for that makes the Large Hadron Collider look like a child's toy. The Large Hadron Collider is the most powerful machine ever built by human beings. It sits in the circular tunnel 17 miles around, buried under the border of Switzerland and France. It accelerates protons to within a fraction of a percent of the speed of light and smashes them together with energies around 10,000 GIA electron volts. The collision sprays particle debris in every direction, and detectors the size of apartment buildings measure what comes out. That machine took decades to design, thousands of engineers and physicists to build, and billions of dollars to fund. It discovered the Higgs boson in 2012. It remains the cutting edge of what humanity can probe experimentally. The Planck energy is roughly 10 million trillion giga-electron volts. The gap between the Large Hadron Collider and the Planck energy is about 15 orders of magnitude, 1,000 trillion times more energy than the most powerful collider ever built. To close that gap, by scaling up the collider in the most straightforward way using the same principles, just bigger, you would need a ring not 17 miles around. You would need a ring larger than the observable universe itself. The observable universe is about 93 billion light-years across. 1 light-year is about 6 trillion miles. The collider required to reach the Planck energy would need to encircle a region that size. This is confirmed by the physics. The numbers are not ambiguous. The Planck scale is so far beyond current technology that no engineering breakthrough, no new accelerator design, no future civilization constrained by the laws of physics as we know them could build a machine to directly probe it. This is why string theory, loop quantum gravity, and every other approach to Planck-scale physics has been forced to look for indirect evidence. Signatures in the cosmic microwave background, subtle patterns in gravitational waves, anomalies in precision measurements of known particles. None of these has produced a confirmed signal from Planck-scale physics. The experimental situation is uncomfortable. Theories about the Planck scale have multiplied for 50 years, but the scale itself remains completely untested. Physics has never been in this position before. Every previous theory in history eventually made a prediction that an experiment could check. At the Planck scale, the experiments may be permanently out of reach. But the Planck scale does not only appear at the limit of what accelerators can do, it appears in a completely unexpected place, inside the mathematics of black holes. And there a connection emerged that nobody predicted, linking the smallest area in nature to the amount of information the universe can store. That connection rewrote how physicists think about reality itself. Here is a number that should bother you. The Planck energy is roughly 10 million GeV electron volts. The energy scale where ordinary matter behaves the way it does, the scale of atoms, protons, and the forces that hold them together, sits around 1000 giga-electron volts. The gap between those two numbers is about 15 orders of magnitude, 1,000 trillion times. That gap has a name. Physicists call it the hierarchy problem, and it is one of the deepest unsolved mysteries in all of science. To understand why physicists lose sleep over this, you need to understand one particle, the Higgs boson. The Higgs boson is the particle responsible for giving other particles their mass. It was confirmed experimentally at the Large Hadron Collider in 2012. Its mass sits at a specific measured value, right at the everyday physics energy scale. That mass should be stable, fixed, but quantum mechanics says otherwise. In quantum field theory, every particle constantly interacts with the quantum vacuum, the seething background of virtual particles that fills all of space. Those interactions add corrections to the particle's mass. For most particles, the corrections are small and manageable. For the Higgs boson, the corrections are enormous. They are proportional to the square of the highest energy scale in the theory. The highest energy scale in the theory is the Planck energy, so quantum mechanics predicts that the Higgs boson's mass should receive corrections roughly the size of the Planck energy squared. That is an absurdly large number. The measured mass is tiny by comparison. For the two to agree, those enormous corrections must cancel each other with extraordinary precision. 1 part in 100 million trillion. That level of cancellation is technically allowed. The math permits it, but it feels deeply wrong. It is like every person on Earth independently rolling a die, and all of them getting the same number. Possible. Wildly implausible. Something unknown is controlling that cancellation. Physicists are almost certain of it. 3 main solutions have been proposed. The first is supersymmetry, a theory that every known particle has a partner particle with slightly different properties, and those partners contribute corrections that automatically cancel the dangerous ones. Clean, elegant, predicted by the math. The second is extraspatial dimensions, hidden dimensions of space so small they have never been detected, which could bring the effective Planck scale down from 10 million trillion giga-electron volts to something much closer to everyday energies. In some versions of this idea, the Planck scale drops all the way to a few thousand GeV-electron volts, right in range of the Large Hadron Collider. The third is conformal symmetry, a mathematical property that some physicists argue could naturally keep the Higgs boson light without requiring any special cancellation. All 3 are theories, none is confirmed, and the place where the evidence should have appeared has already spoken. Loudly. The Large Hadron Collider was not built only to find the Higgs boson. Finding the Higgs was the confirmed goal, the expected discovery. but physicists had a list of what they hoped would follow. Supersymmetric partner particles, signs of extraspatial dimensions, microscopic black holes flickering into existence at the collision point and instantly evaporating in a burst of particles. Any of these would have been a window directly into Planck-scale physics, brought down to observable energies by the mechanisms described in the hierarchy problem's proposed solutions. The Higgs boson appeared in 2012, right on schedule. Then the collider kept running, collecting more data, running at higher energies. The partner particles did not appear. The extra-dimensional signatures did not appear. The microscopic black holes did not appear. By the time the most recent datasets were analyzed, dedicated searches by the two main detector teams had found no evidence of supersymmetry at any of the predicted mass ranges. The simplest versions of supersymmetry, the ones most theorists considered most likely, are now effectively ruled out. More complex versions survive, but they require increasing amounts of fine-tuning to remain consistent with the data, which somewhat defeats the purpose of proposing them as solutions to a fine-tuning problem. The extra dimensions search told a similar story. If the Planck scale were lowered to the 1000 GeV electron volt range by hidden extra dimensions, the collider should have seen microscopic black holes forming. Researchers designed specific analysis strategies to detect the distinctive particle sprays those black holes would produce as they evaporated via Hawking radiation. Nothing. The lower bound on the effective Planck scale in extra-dimensional models was pushed higher and higher, squeezing the parameter space until most simple models no longer solve the hierarchy problem. The collider found the particle it was built to find. Then it looked for the physics that was supposed to explain why that particle has the mass it does, and came up empty. This is an uncomfortable moment for theoretical physics. Not a crisis. Physicists are careful about that word, but a genuine puzzle. The theories built to solve the hierarchy problem have not shown up where they were expected. The Planck scale remains stubbornly unreachable, and the gap between everyday physics and Planck scale physics remains as mysterious as ever. Some physicists argue that the hierarchy is simply a brute fact about the universe, requiring no explanation, similar to the way the universe has the particular constants it has. Others argue that the solution exists but requires a collider even larger than the Large Hadron Collider to expose it. Proposals for a 100-kilometer circular collider are currently being evaluated in Europe and China, and some physicists have started looking in a completely different direction, away from particle accelerators, toward black holes. Because black holes, it turns out, have something very specific to say about the Planck scale. Something that has nothing to do with particle collisions. Something that connects the smallest area in nature to the deepest questions about information, memory, and what the universe is ultimately made of. A black hole is the densest object in the universe. Pack enough mass into a small enough region, and the gravity becomes so strong that nothing, not matter, not light, not any signal of any kind can escape. The boundary of no return is called the event horizon. Cross it, and you are gone from the observable universe forever. For most of the 20th century, physicists thought black holes were simple. They are described by just 3 numbers: their mass, their electric charge, and how fast they spin. Everything else is erased. 2 black holes with the same mass, charge, and spin are physically identical, regardless of what fell in to create them. A black hole made from collapsed stars is identical to one made from collapsed books. The information about what went in, the arrangement of every atom, the content of every page, is gone. Then a physicist named Jacob Bekenstein looked at this more carefully. Bekenstein was a graduate student in the early 1970s. His advisor, John Wheeler, the same physicist who proposed space-time foam, had casually noted a puzzle. If you throw something into a black hole, the entropy of the universe seems to decrease. Entropy is a measure of disorder, of the number of ways a system can be arranged. When organized, low entropy matter falls into a black hole and disappears. The universe's total entropy appears to drop. That violates the second law of thermodynamics, one of the most unbreakable rules in physics. Bekenstein proposed a solution. The black hole itself carries entropy, and the amount of entropy it carries is proportional to the area of its event horizon. Every other object in physics stores entropy in its volume. A box of gas has entropy proportional to how many gas molecules are inside it, which scales with volume. Black holes are different. Their entropy scales with surface area, and the unit of that surface area is the Planck area, the square of the Planck length. When a single bit of information falls into a black hole, the area of the event horizon grows by exactly 1 Planck area. 1 bit, 1 Planck area, every time. Confirmed by the mathematics of general relativity and quantum mechanics combined. That precise connection between the smallest area in nature and the fundamental unit of information is not a coincidence. It is one of the deepest results in all of theoretical physics. It says the Planck length is not only the scale where distance breaks down, it is the pixel size of how much information any region of space can hold, and that pixel has an implication that reaches far beyond black holes. Bekenstein's proposal hit the physics community like a slow-moving earthquake. At first, almost nobody accepted it. The idea that a black hole has entropy seemed absurd. Entropy requires microstates, the underlying arrangements of a physical system that correspond to the same macroscopic appearance. A hot gas has entropy because there are enormous numbers of ways to arrange the individual molecules that all produce the same temperature and pressure. A black hole, by the prevailing view at the time, had no internal arrangements. It was defined by 3 numbers. Where were the microstates? Bekenstein was not able to answer that, but Stephen Hawking, working independently, found something that changed everything. In 1974, Hawking applied quantum mechanics to the region just outside a black hole's event horizon and discovered that black holes are not perfectly black. They emit radiation, a slow, faint thermal glow of particles created by quantum effects near the horizon. This radiation has a temperature, and a temperature means thermodynamics applies, and thermodynamics combined with temperature gives you entropy. Hawking's result confirmed Bekenstein's formula. The entropy of a black hole is exactly 1/4 of its event horizon area, measured in Planck area units. That is a precise, specific formula. Confirmed by the internal consistency of physics, though never directly observed, because Hawking radiation from any astrophysical black hole is far too faint to detect. Now here is the part that took years to fully appreciate. The maximum entropy of any region of space is determined by its surface area, not its volume. Think about that carefully. You have a sphere of empty space. How much information can you pack into it? Physics says the answer is determined by the area of the sphere's surface, measured in Planck areas. 1 bit per Planck area. Fill the sphere with enough matter and energy to saturate that limit, and the sphere collapses into a black hole. The black hole is the maximum information storage state for any given region. The volume is irrelevant, the surface is everything. This was the first hard evidence that the universe might store its information in a fundamentally 2-dimensional way. That the 3-dimensional world we experience might be, in some precise sense, a projection of information encoded on a 2-dimensional surface made of Planck area pixels. The idea that grew from this discovery has a dramatic name, and it suggests that everything you have ever seen, touched, or experienced might be a kind of cosmic hologram. A hologram is a 2-dimensional surface that contains enough information to reconstruct a 3-dimensional image. Run your credit card under light, and a 3-dimensional image appears from a flat surface. The image looks solid, looks like it has depth, looks like you could reach into it. All of that information is encoded in patterns on a flat sheet. In the 1990s, 2 physicists independently proposed that the universe works the same way. Gerard Hooft and Leonard Susskind developed what is now called the holographic principle. Their proposal, the maximum amount of information that can exist inside any region of space, is fully encoded on the boundary surface of that region. 1 bit per Planck area of surface. The inside is determined by the outside. The volume is redundant. Everything that happens in three-dimensional space is a projection of information stored on a two-dimensional Planck scale surface. This is a theory, highly motivated by the black hole entropy result, accepted as almost certainly pointing towards something true by a large fraction of the physics community, but unconfirmed as a complete description of our specific universe. The implication for the Planck length is direct and strange. If the holographic principle is correct, the Planck area is not just a measurement limit or a scale where physics breaks down. It is the fundamental resolution of the universe's information processing. Reality has a pixel density, 1 bit per Planck area on the cosmic screen. Everything inside the volume, every particle, every field, every event is encoded on that surface. At Planck resolution, the interior is derived from the boundary. Three-dimensional space, the space you live in and move through, is a derived concept, an emergent projection. The underlying reality is two-dimensional and pixelated at the Planck scale. Some physicists resist this language because it sounds too much like a simulation argument, and they are right to be careful. The holographic principle does not say the universe is a computer running a program. It says that information, and specifically the maximum density of information, is bounded by Planck area tiles on surfaces. Whether that has philosophical implications about the reality of three-dimensional space is a separate question. What it does say, unambiguously, is that the Planck length appears at the foundation of two completely separate areas of physics, the breakdown of space-time geometry and the quantum information content of black holes and all regions of space. The same number, the same scale, twice. That kind of coincidence, in physics, is never a coincidence. And in 1997, a young physicist proved that the holographic principle is not just an analogy, it is mathematically exact. And his proof connected gravity, quantum mechanics, and information in a way nobody had seen before. Juan Maldacena was 29 years old when he upended theoretical physics. In 1997, working at Harvard, he published a paper proposing a precise mathematical equivalence between two completely different theories. One theory described gravity in a three-dimensional space with a specific curved geometry. The other described quantum particles with no gravity at all, living on the two-dimensional boundary of that space. The two theories were identical. Every calculation you could do in one had an exact translation in the other. Every particle in the gravity theory corresponded to something in the boundary theory. Every gravitational interaction in the interior corresponded to a quantum interaction on the surface. The two descriptions, one with gravity, one without, one three-dimensional, one two-dimensional, produced exactly the same physical predictions. Physicists call this the anti-de Sitter space conformal field theory correspondence, or more commonly, AD/CFT. It is the most cited paper in the history of theoretical physics. What it proved mathematically is that gravity is not fundamental. Gravity in the interior can be entirely derived from quantum information theory on the boundary. Space itself, the three-dimensional stage where gravity plays out, emerges from the quantum entanglement patterns of particles on a two-dimensional surface, and the pixel size of that surface is the Planck area. The boundary theory has no minimum length built into it. It is an ordinary quantum field theory, the kind physicists have used for decades. But when you translate boundary physics into interior physics, the Planck length appears automatically. It emerges from the translation. The Planck scale is not a fundamental input, it is an output. It appears because of the relationship between the two descriptions. This result does not directly tell us that our universe is holographic in this specific way. The AD/CFT correspondence applies precisely to a universe with a specific kind of negative curvature, while our universe has positive curvature from dark energy. Extending the result to our universe is an active research area with progress, but no complete answer. What it does tell us is that a universe where gravity is real and a universe where gravity is derived from quantum information are mathematically indistinguishable. The Planck length sits at the interface of both, and space itself may be built from quantum information, the way a hologram is built from laser patterns on a flat surface. This is a confirmed mathematical result. What it means physically for our universe is an open question, but the Planck scale does not only appear in the birth of space-time and the structure of information, it appears at the death of things, specifically at the death of black holes. And what happens in that final moment is one of the most unsettling open problems in all of physics. Black holes die. Slowly, incredibly slowly, but they die. Stephen Hawking proved this in 1974, and it remains one of the most stunning results in the history of science. He showed that the event horizon of a black hole is not perfectly quiet. Quantum mechanics makes it glow. Here is the mechanism. The quantum vacuum, the state of lowest energy in empty space, is not actually empty. Quantum mechanics requires that pairs of virtual particles constantly pop into existence and annihilate almost immediately. This happens everywhere, all the time. Under normal circumstances, the two particles in a pair appear together and vanish together, leaving no net effect. At the event horizon of a black hole, the situation changes. One particle from a virtual pair can fall inside the horizon while the other escapes to the outside. The escaping particle becomes real. It carries energy, and because energy must be conserved, the black hole loses an equal amount of energy, which means it loses mass. The black hole shrinks. The radiation leaving the black hole is called Hawking radiation. It is thermal, meaning it has a temperature, and that temperature is inversely proportional to the mass of the black hole. A stellar mass black hole, the kind formed when a large star dies, radiates at a temperature so cold it is swamped by the ambient temperature of the universe. Its evaporation time exceeds the current age of the universe by an almost unimaginable factor. But the evaporation accelerates as the black hole shrinks. Smaller mass means higher temperature, means faster radiation. The process feeds on itself. As the black hole loses mass, it radiates faster, loses mass faster, radiates faster still, all the way down to the Planck scale. When the black hole shrinks to roughly the Planck mass, about the mass of a grain of sand compressed into a volume 100 billion trillion times smaller than a proton, general relativity and quantum mechanics both stop making coherent predictions. The same collision that breaks physics at the Planck length breaks it again here, at the endpoint of black hole evaporation. What happens in those final moments is completely unknown. The energy released could be spectacular, a burst of Planck energy radiation. The black hole could leave behind a stable remnant, a Planck mass object that simply persists forever. Or everything could smoothly vanish. Each possibility carries consequences that reach far beyond the black hole itself. The death of a black hole is the most extreme event the universe can produce. By the time a black hole shrinks to the Planck mass, the temperature of its Hawking radiation has climbed to the Planck temperature, the hottest anything in the universe can be described by known physics. At that point, quantum gravity effects completely dominate. The smooth space-time of general relativity no longer exists. The quantum field theory description of Hawking radiation no longer applies. No current theory can say what happens next. Three possibilities are each taken seriously by physicists. The first possibility, a final explosion. As the black hole approaches the Planck mass, its temperature climbs without limit. In the final Planck time, it releases its remaining energy in a burst of radiation. The black hole vanishes completely, leaving nothing. Clean ending. The energy goes back into the universe as radiation. The second possibility, a Planck remnant. The black hole shrinks toward the Planck mass but stops. Quantum gravity effects stabilize it at that scale, producing a stable inert particle with Planck mass, roughly the mass of a grain of sand. This remnant simply persists forever. It does not interact with ordinary matter in any detectable way. If this is true, the universe is slowly filling with Planck remnants, one from every black hole that has ever evaporated. The third possibility, something entirely outside current frameworks. Physics at the Planck scale is genuinely unknown territory. The final state might be something no current theory can even describe, requiring a completed theory of quantum gravity to understand. The Planck mass, as a physical scale, has a specific meaning that makes this moment feel special. It is the mass at which a particle's quantum wavelength, from quantum mechanics, equals its gravitational Schwarzschild radius from general relativity. At the Planck mass, both theories demand equal attention. For every other mass, one dominates. At the Planck mass, they meet. And the Planck mass endpoint carries something even more troubling than the question of where the energy goes. It carries the question of where the information goes. Everything that ever fell into the black hole, every atom, every photon, every quantum state, encoded information about what it was. The black hole swallowed all of it. Now the black hole is gone. Did the information survive? Information cannot be destroyed. That statement sounds like philosophy, but in physics it is a law. Quantum mechanics requires that the complete description of any physical system at one moment determines its complete description at every future moment. If you knew the exact quantum state of every particle in the universe right now, you could in principle calculate the exact state at any point in the future, or reconstruct any point in the past. The information is always there, always preserved. Black holes appear to violate this. An object falls into a black hole carrying its information, the arrangement of its atoms, the quantum states of its particles, the patterns that made it what it was. Inside the event horizon, that information seems trapped forever. Nothing can carry it back out. Then the black hole evaporates via Hawking radiation, is perfectly thermal. Thermal radiation carries no information. It is the physics equivalent of static. A black hole formed from a collapsed encyclopedia and a black hole formed from a collapsed star, if they have the same mass, charge, and spin, emit identical Hawking radiation. The encyclopedia's information is gone. That violates quantum mechanics. You cannot have both. A black hole that destroys information and a universe that obeys quantum mechanics. One of them must be wrong. This is the black hole information paradox. It has been debated for 50 years. It was the central argument in a famous bet between Stephen Hawking, who believed it was preserved, and John Preskill, who believed it was preserved. Hawking conceded the bet in 2004, accepting that information is likely preserved, but the mechanism, the precise way information escapes the black hole and gets encoded in Hawking radiation, remains unknown. The Planck scale sits directly in the middle of this problem. If information escapes, it must do so through the Hawking radiation emitted over the entire lifetime of the black hole. The final moments of evaporation, when the black hole shrinks to Planck scale, may be the critical phase. Perhaps the last burst of Planck energy radiation carries encoded information about everything that ever fell in. Perhaps quantum gravity effects scramble and re-emit the information in ways no current theory can track. The holographic principle suggests information is preserved on the event horizon and gradually encoded in outgoing radiation, but the precise mechanism at Planck scales is an open question. Unresolved, active research, no consensus. What is agreed on is this: the answer lives at the Planck scale, and the Planck scale as of now remains beyond the reach of any direct measurement. But in 2023, something shifted. A research team made a discovery that extended the Planck scale endpoint of black hole evaporation to objects nobody had expected. Objects like planets, like stars, like you. For 50 years, Hawking radiation was considered a property of black holes. Specifically, it was tied to the event horizon, the point of no return around a black hole. The standard explanation required an event horizon to exist. Virtual particle pairs split at the horizon. One falls in, one escapes. The black hole loses mass. No event horizon, no Hawking radiation. In 2023, a team of researchers at Radboud University in the Netherlands published a result that changed this picture. Michael Wondrak, Walter van Zuilichem, and Heino Falke showed mathematically that the mechanism producing Hawking-like radiation does not require an event horizon. It requires only curved space-time. Any mass curves space-time around it. The Earth curves space-time more strongly. A neutron star curves it more strongly still. Wherever space-time is curved, virtual particle pairs can be separated by the curvature itself, even without a black hole's extreme gravity. One particle escapes. The object loses an infinitesimal amount of mass. The rate is unimaginably slow for ordinary objects. For a mountain, the evaporation time would exceed the current age of the universe by factors beyond comprehension. For a planet, longer still. The effect is real, but completely unmeasurable with any current or foreseeable technology. But the physics says it happens. Everything radiates. Everything loses mass, with agonizing slowness, through a Hawking-like process driven by the curvature of its own space-time. And every object's evaporation ends at the same place, the Planck scale. As any object loses mass through this process, it shrinks, its temperature climbs. Eventually, after times that make the current age of the universe look like a blink, every massive object in the universe reaches Planck mass scale, and there, the same unknown final state that governs black hole evaporation takes over. The universe ends, in this picture, not with a bang or a freeze, but with every remaining object dissolving one Planck mass remnant at a time, across a time span that language cannot adequately describe. This is a confirmed mathematical result, published and peer-reviewed. It does not violate any known physics. The evaporation rates for ordinary objects are so slow they are undetectable, but the direction of the arrow is real. Everything in the universe is heading, with complete inevitability, toward the Planck scale. And at the Planck scale, physics currently has nothing left to say. But the Planck scale creates a conflict that most people have never considered. A conflict between two pillars of physics that should be compatible but turn out to be quietly at war with each other. A conflict about what happens when you move very fast past a Planck-length object. Einstein's special relativity is built on one absolute, the speed of light. Light travels at 186,000 miles per second in empty space. It does not matter how fast you are moving relative to the light source. You can chase a beam of light at 99% of its speed, and you still measure it moving away from you at 186,000 miles per second. The speed of light is the same in every reference frame. That is confirmed, tested, foundation of modern physics. One consequence of special relativity is length contraction. Objects moving at high speeds appear shorter in the direction of motion from the perspective of a stationary observer. The faster the object moves, the more it contracts. At speeds approaching the speed of light, the contraction becomes extreme. Now here is the problem. The Planck length is supposed to be the minimum meaningful distance, a hard floor on how small anything can be. But if an object moving at high speed appears length contracted to a stationary observer, then an object with a resting length of exactly one Planck length, viewed by an observer moving fast enough relative to it, would appear shorter than one Planck length, below the supposed minimum. This creates a direct contradiction. If the Planck length is a true minimum, it cannot contract. If special relativity is exactly right, it must contract. One resolution is that the Planck length is only a measurement limit, not a true minimum. At that point, no contradiction exists because there is no hard floor to violate. Another resolution is more radical. A theoretical framework called doubly special relativity modifies Einstein's transformation equations to make two quantities observer independent instead of one. The speed of light, as always, and the Planck length. In this framework, no matter your reference frame, you always measure the Planck length as the same size. Length contraction stops working at the Planck scale. The equations of special relativity receive corrections that become important only at energies near the Planck energy. This is a theory, speculative, contested among physicists. No experiment has detected the corrections that doubly special relativity predicts, because those corrections become significant only at Planck energies, which are unreachable by current technology. But the conflict it addresses is real. The Planck length and special relativity are in tension. Resolving that tension without breaking either, one requires new physics. And new physics at the Planck scale is exactly what every approach to quantum gravity is hunting for. Gamma-ray bursts, detected from across the observable universe, have become one of the most powerful tools in this hunt. And the results are startling for reasons that cut both ways. When a massive star collapses into a black hole or neutron star, the explosion is the brightest event in the known universe. A gamma-ray burst releases more energy in a few seconds than the sun will radiate over its entire 10 billion-year lifetime. The light from these explosions travels across billions of light-years and arrives at Earth carrying photons with an enormous range of energies, from low-energy radio waves to extremely high-energy gamma rays. This makes gamma-ray bursts perfect natural laboratories for testing Planck-scale physics. The logic is the same used for the space-time foam search. If the Planck scale modifies the way photons propagate through space, different energy photons should travel at slightly different speeds. A tiny difference, accumulated over billions of light-years, might become detectable. Doubly special relativity predicts exactly this kind of energy-dependent speed. Space-time foam models predict it. NASA's Fermi Gamma-Ray Space Telescope detected a gamma-ray burst in 2009 from a source about 7 billion light-years away. The burst produced photons spanning an enormous energy range, arriving essentially simultaneously. Analysis showed that any energy-dependent speed difference was smaller than 1 part in 10 to the 21st power of the speed of light. That constraint is extraordinary. It rules out the simplest linear versions of doubly special relativity. Photons of vastly different energies, after 7 billion light-years of travel, arrived within fractions of a second of each other. Special relativity, in its standard form, held. A subsequent observation by the Very Energetic Radiation Imaging Telescope Array System pushed the limit even further. A photon with 250 billion times the energy of visible light arrived from a blazar with no detectable time lag relative to lower energy photons. Standard special relativity survived again. These are confirmed observational results. They have not ruled out all Planck scale modifications to relativity, because some models predict effects too small for current instruments to detect, but they have eliminated the largest predicted effects and placed tight bounds on any remaining ones. The universe, used as its own telescope aimed at itself, keeps finding that space-time looks smooth, that light behaves uniformly, that no Planck-scale granularity has left a detectable trace in the cosmic record. That negative result is itself a profound clue. And it connects directly to a problem at the very beginning of cosmic history, where the Planck scale may have left its deepest fingerprint of all. Every galaxy you can see in the night sky grew from a seed, not a physical object, a quantum fluctuation, a tiny random ripple in the density of energy in the early universe, smaller than an atom, smaller than a proton, arising from quantum uncertainty itself. Those ripples were stretched by inflation, the period of exponential expansion in the universe's first fractions of a second, from quantum scale to cosmic scale, stretched until they became the density variations that gravity then amplified into galaxy clusters, filaments, and the large-scale structure of the universe. This mechanism is confirmed. The pattern of temperature variations in the cosmic microwave background, measured with extraordinary precision by the Planck satellite and its predecessors, matches the predictions of inflationary quantum fluctuations with stunning accuracy. The seeds are real. The stretching is real. Here is the problem. Run the expansion of inflation backward in time. The seeds that became galaxy clusters were stretched from very small scales. Run far enough back, and those seeds, before inflation stretched them, were smaller than the Planck length. If the Planck length is a true minimum, the seeds should not have been able to exist at subplanckian scales. Physics does not describe what they were doing there. The theory of inflation, which describes the stretching, must start from initial conditions that sit below the scale where inflation's own theoretical foundations hold. Physicists call this the transplanckian problem. It is unresolved. Several responses exist. Some physicists argue that inflation began from fluctuations just above the Planck scale, and the math works out without anything subplanckian. Others argue that the transplanckian regime does affect inflation, and that subtle imprints of Planck scale physics might be detectable in the cosmic microwave background as tiny departures from the standard predictions. If those imprints exist, they are extraordinary things. They would be direct observational signatures of physics at the Planck length, carried across 13 billion years of cosmic history and encoded in the temperature pattern of the oldest light in the universe. Every galaxy, every star, every planet would be a stretched copy of a structure that once existed at the smallest scale nature permits. Current measurements have not found such imprints. The next generation of telescopes and cosmic microwave background experiments will push the sensitivity further. The Planck scale may have left a message in the oldest light. We are still learning to read it, and the challenge of reading it brings into focus a deeply uncomfortable truth about where physics stands today. The tools we have built to measure time, our best clocks, our finest instruments, are so far from the Planck time that the gap staggers the imagination. Atomic clocks are the most precise measuring instruments humans have ever created. The current best optical lattice clocks using strontium or ytterbium atoms measure time by counting the oscillations of light emitted when electrons in those atoms jump between energy levels. Those electrons oscillate hundreds of trillions of times per second. The clocks are accurate to roughly 1/10,000,000th of a trillionth of a second. That level of precision has real applications. The GPS satellites orbiting Earth rely on atomic clocks. Without their extraordinary accuracy, your phone's navigation would drift by miles within minutes. The clocks are so precise that physicists use them to detect the gravitational time dilation predicted by general relativity. A clock slightly higher up, farther from Earth's center, ticks measurably faster than one closer to the ground. Now consider the Planck time, approximately 5 × 10⁻⁴ seconds. The best atomic clock measures time to about 1/10,000,000th of a trillionth of a second. Expressed as a power of 10, that is roughly 10⁻⁻19 seconds. The Planck time is 10⁻⁴ seconds. The gap between them is 25 orders of magnitude. 25 orders of magnitude means 100 trillion times shorter than the finest temporal measurement humans have ever made. To put that gap in perspective, 1 second compared to 10 million times the current age of the universe is a gap of about 25 orders of magnitude. The interval between our best clock and the Planck time is the same ratio as 1 second to the lifetime of 10 million universes. Every physical event, every particle interaction, every quantum transition that humans have ever measured has happened at timescales comfortably above the Planck time. Nothing in experimental physics has ever approached it. The Planck time is not an engineering challenge. It is a conceptual wall. The measurement difficulty does not decrease with better technology on any foreseeable trajectory. And yet this extreme remoteness has not stopped physicists from asking what happens there, because the Planck time is where time itself may stop being a meaningful concept, where the smooth flow of moments, the thing that gives causality its direction, may dissolve into something no human language currently has words for. The question of what the Planck time means for the nature of time is deeply connected to an even broader question, whether the concept of smaller than Planck means anything at all. And the answer from one major branch of physics is as strange as any result encountered so far. In everyday life, smaller always means something. Half an inch is smaller than an inch. Half a proton width is smaller than a proton width. The concept of smaller seems infinitely extendable. You can always take half of whatever you have. String theory says that at the Planck scale, this stops being true. Specifically, it proposes that asking about distances below the string length, which sits near the Planck length, is not just experimentally impossible, but physically meaningless. The question has no answer because the universe contains no fact corresponding to it. The argument comes from a mathematical property called T-duality. In string theory, some spatial dimensions are compactified, curled into tiny circles. The radius of those circles is a length. T-duality states that physics with a compact dimension of radius r is mathematically identical to physics with a compact dimension of radius equal to the string length squared divided by r. Small radius and large radius are dual to each other. They produce the same physics. This means that as you shrink the compact dimension below the string length, you are not entering new territory, you are mathematically returning to the same territory you left when you crossed the string length from above. The physics folds back on itself. Substring length distances are not a new, smaller regime. They are a mirror image of superstring length distances. The concept of smaller than the string length does not correspond to a new physical situation. It maps to a known one. The question dissolves. This is a remarkable claim. It says the universe has a minimum meaningful length, and asking what lies beyond it is like asking what lies south of the South Pole. The question is grammatically valid. The universe has no answer for it. Loop quantum gravity reaches the same practical conclusion from a different direction. In that framework, space is made of discrete nodes. There is no subplanckian distance because there is no between nodes. The question of what is between two adjacent nodes is like asking what is between two adjacent integers. There is no integer between 3 and 4. There is no distance between two adjacent spin network nodes. Both theories, built on completely different mathematical foundations, converge on the same conclusion. The Planck length is a floor below which the concept of distance either folds back on itself or simply ceases to apply. Whether this conclusion is correct is unknown. String theory and loop quantum gravity are both unconfirmed, but both make the same prediction about the nature of the floor, and that prediction will define one of the central questions of physics for decades to come. The ultimate form of that question is the one that everything in this story has been building toward, the question that has never been answered and may be the most important question in all of science. Everything rests on an assumption. Every equation in general relativity, every calculation in quantum field theory, every model of the cosmos, from its earliest moment to its final evaporation. All of it assumes something about the nature of space, something that has never been tested at the scale where it matters most. The assumption is that space is continuous, that between any 2 points, there is always another point. That distance is infinitely divisible, that the fabric of the universe has no grain, no pixel, no minimum unit below which the concept of location stops making sense. This assumption has worked extraordinarily well. Every experiment conducted in the history of physics is consistent with it. Every measurement, every prediction, every confirmed discovery. The assumption has never failed. But the experiments have never reached the Planck scale. The assumption has never been tested where it counts. If space is continuous, then the Planck length is a measurement limit, not a physical boundary. Something exists below it, permanently hidden from observation, but real. The universe extends downward without end. Infinity goes all the way. Zeno's series never stops. Every journey is composed of infinitely many steps. If space is granular, the universe has a resolution, a pixel size, a shortest distance, a minimum tick of time. Motion is ultimately discrete. Reality is digital at its foundation. and the picture we call three-dimensional space is assembled from Planck-scale chunks, the way a photograph is assembled from individual dots. Both pictures are self-consistent. Both are compatible with every experiment ever performed. Both make predictions that differ only at scales currently unreachable. The stakes are profound. If space is granular, then the smooth equations of general relativity are an approximation, accurate at large scales the way a smooth ramp is an approximation of a staircase seen from far away. The true underlying theory is discrete. Quantum gravity is fundamentally a theory of Planck-scale chunks. If space is continuous, then the breakdown of physics at the Planck scale is a failure of our theories, not a feature of reality. Somewhere below the Planck length, a completed theory of quantum gravity continues to make predictions, and the universe carries on without any minimum step. Physicists are pursuing both possibilities simultaneously. Experiments with gravitational wave detectors look for tiny departures from smooth spacetime. Quantum sensors probe the boundary of what time measurement can achieve. The next generation of cosmic microwave background surveys searches for Planck-scale imprints in the oldest light. Theorists on both sides build more precise predictions, waiting for data that might tip the scales. The answer may arrive in 10 years. It may take a century. It may require a technology nobody has imagined yet, something as far beyond the Large Hadron Collider as the collider is beyond a child's magnifying glass. What is certain is this: the question is real. The Planck length is real. The wall it marks is real, and on one side of that wall sits everything physics has ever successfully described. On the other side sits everything we do not know.